All right, so I want to go back and hit the high points of this because of yesterday. We're a little bit behind, so I want to make sure that I'm caught up to where we were. Density. If you know the definition, awesome. That's all fine and well, but I need you to be able to apply the definition. Today we're going to see a little bit more about what the definition of density is. Remember, the density is mass divided by volume. You can write it in that, or we can plug it into the triangle, and we're going to work with that today if we hopefully get to it. So we've gone through all this, right? Okay, good. Great. This. Okay. If you didn't get this, make sure. Hang on one second. Okay, so what I was saying is that if you did not highlight or circle or star this, please make sure you know that fact. We're going to talk about that today. So if I have 50 grams of water, okay, 50 grams of water, I'm going to come off this. So we know that density is equal to mass divided by volume. And if I have 50 grams of water, the first question I need you to know is how many milliliters is that? 50, because remember, it's a one-to-one relationship. What's the density? 1. Okay. What if I have 1,000 grams of water? How many milliliters? 1,000. What's the density? 1. So no matter how much water you have, is the density always going to be 1? Yes. Okay, so that's the important thing I need you to know. We're going to get more in depth with that soon. Okay, so that's the first part. So floating and sinking. So that rubber duck, we know it floats, but what property is floating and sinking based on? Very good. So up here beside this in your notes, right, based on density. Okay, so we know if something floats or sinks if based on its density. And what you have to do is you have to compare the two objects. So that rubber duck is floating on water. So how would its density compare to the density of water? It's what? It's less. Very good. So come on now. If I throw this mouse across the room, don't be scared. Okay. So less dense materials will float on top of more dense materials. Does it just have to do with water? Now we'll talk about a little bit more about that later on. So what about these rocks? In terms of their density, what do we know about the density of a rock? It's more than 1. Very good. So objects that are greater than 1 sink. Objects that are more than 1 will float. Now, what about objects that are exactly 1? That's a good. So objects that are exactly 1 will float in midwater or at whatever level you leave the object. Okay, so you can just put it in the middle of the water and it'll just stay there. It's going to stay in that exact location. And we're going to do a density. It's like a virtual lab kind of thing where we can put different objects in water and we see how they float or how they sink. And there will be some of the blocks that you put in the water and they literally just stay there. They don't go up, they don't go down, they stay in the middle of the water. And you should know what the density of those things are based on that. Now it says fish and submarines control their depths by changing their density. How would a fish control its density? Very good. An air bladder. Okay, what is an air bladder? What does it mean? Okay, so the water comes over the gills. Okay, and what does it get out of the water? Oxygen. Okay, so what it does is it takes that oxygen and pumps it into an air bladder. Well, what happens if the fish wants to go to the surface? What does it have to do with that air bladder? Because what happens whenever you have a bigger space? It expands, right? You have more volume, so it's going to make you rise. What does a fish do whenever it wants to go to the bottom? Well, lets all the air out and it starts to begin to sink. Submarines do the exact same concept. However, they're mechanical. They're not just natural air in, air out. But they do the exact same thing, so they can rise and fall based on their density. Okay. So Titanic. Its maiden voyage, before it ever hit the iceberg, we're talking about when it was sitting in port and everybody was getting on it. What is the density of this enormous still-hulled ship full of machinery, coal, people, and all sorts of heavy things? How in the world can this big, huge, amazingly large ship have a density of less than 1? What? But the density is still 1. It's still water. Now, it's obviously salt water. And the salt water's density is a little bit more, but it's still going to be, it's got to be less than salt water, less than water, so it can float. It does have something to do with how water displacement and the buoyancy. But how can this be? What about its hollow vessel? Okay, it's hollow vessel. It's not a solid object. How many of you have been on a cruise? Okay, if you've been on a cruise, you understand how big these ships are. And the ones nowadays make the Titanic look like a yacht that sits in a small port. Okay, the ones nowadays are absolutely massive, but they all still float. So here's what happened: the Titanic hit the iceberg. What began to happen to the hull of the vessel? Began to fill with water. Well, did the space the vessel took up change? No, but did the mass of the vessel begin to change? Well, as the mass went up and up and up, what happened to the ship within the water? It started to get lower and lower and lower. Okay. Now, the reason, and you've all seen the movie, the reason that it tips up is because it started filling in the front compartments, right? So it didn't fill evenly, so it went from compartment. So the front end was heavier than the back end. So that's why it did tip up. So after it filled with water, what began to happen to its density? It went greater, right? It started getting closer and closer to 1, and then once it took on enough and it exceeded 1, what happened to the ship? It sank. Okay, and so now sitting on the ocean floor, what would have to be its density? More than 1. We don't know what it is, but at least it's more than 1. Several years ago, they actually talked about extracting the ship back to the surface, but as soon as they started doing a little bit with it, it started falling apart. So they said, we're not going to try to do that. So it will always and forever be at the bottom of the ocean. Okay, so comparing densities. We've got this thing called a density column. And in this density column, there's wood, corn oil, plastic, water, a tar ball, glycerin, rubber washer, corn syrup, copper wire, and mercury. Okay? What property are all of those things separated by? It's density. So my question to you is, where is the most dense object? At the very bottom. Okay? So where is the least dense object? At the top. So I have a question. What if you took that column and you corked it and you shook it, okay, and you got everything all mixed up? Say you sat it overnight and you came back the next morning. Would it still be mixed up? What would happen to it? It would look just like this. Same concept with muddy water. You take a cup full of muddy water and you set it on the counter overnight. When you come back, what's it look like? The dirt's on the bottom and the clear water's at the top. Why does it separate? The density. It separates based on its density. Go ahead, Cody. I mean, you can pour it from a container. No, you can touch mercury, but you cannot ingest mercury. Back in my parents' day, they said they would just get mercury out and just pour it in their hand and play with it, like before they realized how extremely dangerous it was. But yeah, mercury is very toxic. Very toxic. Okay. So, density review. Now, this is a silly question, and I get silly answers, but it's really a straightforward question. We don't actually count G's. A minute ago, we had to count those letter G's to find the mass of an object. How would you find the mass of a rock? What would you do? The mass of it. Put it on a balance. The mass of it, right? You just use a balance, okay? But how would we find the volume of that said rock? Water displacement, very good. Now, earlier I did this for one of my other classes, and I should have done it for you guys, but I didn't realize I had it. Okay, so that's what you can do. And then how would you find the density of either one of those two? Find the mass, divide it by the volume, right? Go ahead. I mean, you don't say that and then not ask. Okay, thank you. All right, so this is the next slide. Just ask. That's actually a really interesting question. That's not a bad question. If you took all of the fish, let's not say the ocean. Let's say a lake. Let's use Lake Eufaula as an example. Okay, if we went to Lake Eufaula and we took all of the fish, all the alligators, all the snakes, all the gross stuff out, what would happen to the water? It would go down by a whole lot, right? Okay. Now, have any of you ever been to Lake Martin? Lake Martin, yes. If you know what I'm talking about, Lake Martin, by the rock that it jumps off of. Okay, they have actually caught catfish at the bottom of that lake that are bigger than most humans. Catfish. Okay, they're huge. So if you pulled all the fish out of that lake, again, the water would definitely have to go down. So it's an interesting concept that it's uncalculatable, but it's an interesting concept. All right, make sure you get this. This is the next slide. Okay. Now, time is one of the only things that it's one of the few things that we don't use the metric system in full effect. And what I mean by full effect is that we don't use the prefixes like all of the other systems. Like with meter, you've got centimeter and millimeter and kilometer and decameter and all that kind of stuff. With computer stuff, you have bits and bytes and megabytes and gigabytes and terabytes. But with time, really the only two metric prefixes you see with time is a millisecond and a nanosecond, and even those are rare. But with time, we have other things. We have minutes, we have hours, we have days, we have years. So, but you kind of understand what time is. Now, don't put this up because we're going to write two more things on this next slide that I want you guys to write. Okay, so don't put it up just yet. I know it's the last part, but don't put it up. Temperature is another one that we don't use the metric prefixes on. We never call it a kilo Celsius. It just doesn't sound right. We just say that's 1,000 Celsius, which is extremely hot. But again, we don't use the prefixes with temperature either. Now, I'm just going to say this, and I'm not going to get into it. I don't want to get into it, so don't ask me to get into it. But I'm just going to say it for you to absorb it. That first sentence where it says how hot or cold, hot and cold do not exist. It doesn't exist. Hot and cold are arbitrary relative terms. And we'll talk about that later. Now, the unit is Kelvin. We don't have to use Kelvin. What's the other one we can use in science class? Celsius again. And I know that temperature is one of the hardest things for students to really understand. I showed you all that video of Americans trying to use the metric system. So if we walked up to someone on a random street corner and we said, how would you dress if it were 22 degrees Celsius outside? Most people don't know, when you say regular, what's regular? Like this. Okay, I mean, 22 degrees Celsius is in the low 70s. Okay, so this would be an appropriate thing to wear. But most people, when they hear 22 and it's in reference to temperature, what do they think? They think really, really, really cold, but they don't understand the unit concept of how it works. So that is one of the hardest things for students to actually know is the Celsius Fahrenheit difference. So down at the very bottom it says to find Kelvin, add 273. I don't like words when it has to do with calculations, so I want you guys to write this for me. So to go from Kelvin to Celsius, we do 273 degrees, excuse me, that's wrong, 273 plus degrees Celsius. So if it's 30 degrees Celsius, what is that in Kelvin? 303. Okay, 303. Now, basic simple math. What if I tell you that it's 283 Kelvin? How do you get to Celsius? You subtract. You just want to make sure that you can go both ways. It's a very simple thing. Okay. The last thing that I want you guys to write is this. Now, that is a 0. Absolute 0 is 0 Kelvin. So what I'm trying to get you to understand is that Kelvin will never, ever, ever, ever be negative. You cannot have a negative Kelvin. It does not exist. Okay? But what is absolute 0? What does that mean, Ralston? That is true, but give me more specifics. Jackson? Okay. I like that. He said everything stops moving. Now, I need to get a little bit more specific. What do you mean by everything? Hold on, Jackson. What do you mean by everything? What'd you say? Atoms. Now, do atoms make up everything? Yes. But I need to be even more specific than that. What part of the atom stops moving? Electrons. Okay. What are electrons doing around an atom? Constantly spinning. So when we hit absolute 0, all motion or all energy ceases to exist, because is motion a form of energy? Yes, okay? So absolute 0 means that there is 0 motion, there is 0 energy. And here's why I feel that this is an odd theory for people to try to find out. I will tell you, the scientific community has not achieved that value yet. We're really close, but we're not there yet. The atoms are still vibrating. They're not spinning, but they're vibrating. They're trying to get it there. So here's my question to the community that's trying to do this. Y'all have heard the law or the theory that energy can never be created nor destroyed. Well, if you think about it, if you stop all electrons, what have you done with energy? You destroyed it. And so, again, this is just me kind of hypothesizing in my own head of how all this stuff kind of works. Is this thing actually ever real? Can we ever make electrons stop moving? And if that's the case, where does all the energy go? Cody? I have no idea. Now that I don't know, Brad. Okay. Cryogenesis? Is that what you're trying to talk about? I don't know if I believe that. I agree with that. Man, that is one of those, did the chicken or the egg come first? Like, but how can absolute 0 happen really fast? It can't be something instantaneous. You can't create something out of nothing. Are you sure? What's inside of a black hole? Are you sure? Are you sure? We don't know. It could be another universe on the other side of that thing. Matter of fact, the other day I saw an article on some news site that said they finally saw something, and they don't know what it is, but light was shot out of a black hole. They don't know where or how or what it was, but they're monitoring a black hole and something came out of it. They've never seen it before. They finally saw it. Okay. All right. Somebody, Kyron, you had a question? Kyron, question? Grace, we come get these. Come get these. Yeah. Count how many you need and pass them back, and then pass them to Jackson and count how many you need. Yes, sir. The electrons. All right, in just a second, you should be receiving this sheet. I'm also going to pass around the hole punch. Grace, we come get this one. So if you want to hole punch it, you can hole punch it. Here's what I need you to do. Thank you. Actually, put them right there for me. In the top right-hand corner, I need you guys to do this. Now, this is going to become very important to you over the next few days. Okay. As far as the density triangle, what do we plug in where? Okay, top is mass, bottom left, and volume right there. By the end of this sheet, we're going to be able to use this and manipulate it in many different variables. Before we look at a problem, I want to talk about the sheet as a whole and the stuff that's in it. Obviously, all the problems are on the left, but in those two boxes, there's something that's important because we're going to need what's in those boxes. It gives you a substance, and then it tells you what its density is. What's up? Yeah, okay. There are going to be some questions that refer to specifically to certain substances. So if it asks you about styrofoam, and you need the density of styrofoam, it's on that list. Okay. If it asks you about a block or a brick or a cube, it gives you the volume equation for those things. It gives you the volume equation for a cylinder, and it gives you a volume equation for a sphere. So when you get to these questions and you have to do one of those things, it's all up there in that box. So everything that you need is on this sheet to be able to work it out. So the first few problems are very simple. So let's look at number one. Okay, a 13.2 milliliter rock weighs 47.6 grams. Determine its density. One of the things that I have learned over the years of teaching is that students don't know how to read the question. Now, this is really simple. This is straightforward. But when you guys get on the more challenging test and you get on the ACT, you don't know what the question is asking you to solve for. So understanding what they need as an answer is very crucial. So I'm always going to ask you a question about the question. And my question to you is, what is the question? I know that was a lot. The density. You're trying to solve for the density. That other garbage does not matter. Because if you don't know what density is, you can't do this. I need you to be able to figure out, what are we looking for? What's the whole purpose of doing this? The whole purpose is to find the density of this rock. Now, you do know something about density, and so we can figure it out. So what is the formula for density? Very good. So mass divided by volume. The second thing that I've noticed about students when they start doing this stuff is they may know a formula, but they're not quite sure what goes where or how to plug it in, especially if it's not directly and explicitly stated. Because anywhere in that question, does it have the word mass? No, but it does have a similar word, and what word is that? Grams. No, excuse me. Weighs. Weighs, mass, kind of the same concept. They use it interchangeably, even though it's technically not right, but that's fine. So if that word wasn't there, you might not understand what it is. So if you understand units, can you plug them in? Because is there a word volume anywhere in there? But if you know what milliliter means, then you can plug it in. So based on the two data points that I have been given, are those two things good enough for me to plug in as they're currently written? Yes. All right, so let's plug them in. So now, my first question is, which value goes on top? Okay, 47.6 grams divided by 13.2 grams. Now, this is something that we're going to talk about significant figures. Significant figures. I'm telling you now, I'm going to teach this later, and every year when I teach this, every student that I teach knows how to do this by the end of it. It is a very, very simple task. All you have to do is count some numbers. As we go through this, I'm going to tell you what the answer is in the correct number of significant figures. And you're going to look at me the first few problems and say, huh? I'm not expecting you to get it. I'm wanting you to analyze and think, all right, how did he come up with that potential number of significant figures based on the data in the question? Because here's my question to you, Cody. I'll come right back to you, okay? When you do this, come on. When I take this and I plug, by the way, and I haven't said this, if you have a calculator, now's a great time to go ahead and get it out. If you have a calculator in your locker or you have it at home, you need to start bringing it with you. We're going to be using it a lot over the next several days and weeks to come. So please make sure you have a calculator with you. The reason I want you to make sure you have one is because when you get on the test, you're not allowed to use your phone. And your phone is not a sufficient scientific calculator. Yes, it can do some of these fancy things, but you need to be able to learn how to use your calculator. on the test. Okay, so 47.6 divided by 13.2 equals. Does it make sense to write that entire thing down? No, that's ridiculous. Okay, never, ever, ever write the entire value in the calculator down unless it is already given in the correct number of significant figures. Just throw it at me. I just want you to talk to me. No. My question is, if that popped up in your calculator, what would you write? Okay. I hear 3.60. Would anybody just stop at 3? Would anybody stop at 3.6? And this, I don't care. I'm just asking. This is what you tell me what you would do if you saw that. How many of you stop at 3.6? Excuse me, 3.60. All right. Would anybody round it to 3.61? All right. Would anybody go 3.606? Would anybody go beyond that? If you go beyond that, that's a little much. Go ahead, Cody. Okay. I'm with you on that. But here's the correct answer and the correct number of significant figures. Not the 8. The 6 after the 0. It does like an 8. It is a 0. Hold on, guys. Hold on. If you left your answer as I have written it over there in orange, would you get credit for that answer? You would lose all credit for that. You can set up your work, you can write it as beautiful as you possibly could, but you would lose credit for that because what's missing? The units. I did write grams on there. That is my mistake. Thank you for catching that. I need to write milliliters. What's up, Ian? Dorian? Okay. So my question to you is, do those two units cancel each other out? No. So I must make sure that they maintain in my unit. So it is 3.61 grams per milliliter. Now I know exactly what you're talking about. Cody, go ahead. Yeah. Thank you. All right, James. No idea. No idea. Yes. Yes, that will actually sink. The gas would go below the... Now, what gas that is, I mean, you can Google it. What gas is more dense than water? Just look it up. There is a gas, I know for a fact, that is called... it's called sulfur hexafluoride. And you know how if you inhale helium, it makes your voice go up? If you inhale this stuff, it makes your voice go down an octave. So you talk like really, really, really deep. Sir? So the floating tinfoil? Yeah. The Spangler or Ellen DeGeneres or something like that? Yeah. Okay. So what? Yep. What you can do is you can take a box and you can, it'd be just like, I mean, y'all been to the grocery store and they have those balloon things where you put the balloon and it blows it up. Same kind of concept, but there's a hose, and what you can do is you can put the hose down in the box, and when you pump that gas in, it's odorless and it's colorless, so you can't see it. You don't even know it's there. But it is more dense than the surrounding atmospheric air, so it will settle. But that box will trap it in. And so what happens is you can put things that are less dense than that gas, and aluminum foil is actually less dense. And so that aluminum foil will actually float on top of that gas. And it looks like it's floating in midair, but it's because you can't see the gas. So it's actually kind of neat, but it's sulfur hexafluoride is that gas. Now, I don't know about the water thing, but I know there are some gases that are more dense than atmospheric air that will actually sink in atmosphere. They go to the bottom. I mean, it's not great for your vocal cords, no. But same concept with helium. It's not great with helium either. All right, so let's look at the next one. Okay. 138.42 grams of salt water has a volume of 117.0 milliliters. Determine its density. What are we solving for specifically? The density. All right, so we now know that the density is mass divided by volume. Now, based on the values that are given in the problem, are they already in their appropriate units to be plugged in? Yes, okay, so let's plug them in. So 138.42 grams divided by 117.0 milliliters. Okay, so that is going to be our value. So let's plug it in the calculator and let's see what we get. Okay, clear. 130. Now, again, it would make absolutely no sense to write that entire number down. So, my question to you is, again, you don't know this at this point. I don't expect you to know. But as we go through this, some of you are going to pick up on significant figures, and you're going to know before I even teach it. But if you don't pick it up, that's fine. I'm going to teach you, and it is really simple. And when you go back and look at this, you'll understand exactly why we did what we did. So how many of you would stop at just 1 as your answer? How many of you would go 1.1? All right, and the same concept, 1.2. Okay, how many of you go 1.18? Would anybody go 1.183? That's what I would do. That is your answer in correct significant figures. And again, if you don't understand, it is perfectly fine. So it is 1.183. And just like I asked a minute ago, if you left it like that, would you earn full credit? Nope. What you got to throw on the end of it? Grams per milliliter. Now, I'm going to ask a question. I'm going to give you a chance to work on this one. The next one says 0.446 grams of hydrogen gas fills a 5-liter bag. Determine its density. I need to ask this question at this point. Does the volume unit look a little odd at this point? My question to you is, what is the definition of density by equation? What's the equation of density? Mass divided by liter. Is it a volume unit? Then leave it alone. Plug it in as it's written. So your unit would not be grams per milliliter, it would be grams per liter. So if it's ever already in a volume unit, leave it alone. Don't mess with it. You can change it if you want to, but don't. Leave it alone. Okay? So go ahead and see if you can solve for that answer. And see if you can get the right number of sig figs. Again, I don't expect you to get it right, but if you do, that's good. Just put it right there, homie. Thank you. Appreciate it. Okay. All right, so what are you solving for specifically? What's the question about? The density. So we've got mass divided by volume. We know that the mass is 0.446 grams. We know that it is 5.0 liters. That is a G at the end. Wheel her in, please. I think the door is shut. So let's pull up our handy dandy calculator. Clear this. 0.446 divided by 5 is equal to that. Now, this is where significant figures are going to throw a curveball at you. How many of you wrote 0.08? Okay. How many of you wrote 0.09? How many of you wrote 0.089? How many of you wrote the whole thing? Okay. Again, I don't expect you to know this yet, but here's the correct answer in the correct number of significant figures. It is 0.089. Okay. And again, I don't expect you to have this perfected yet. So before I go any further, I do want to go back and show you something. I'm going to write it in brown. This orange number is 3 significant figures. This red number is 4 significant figures. This green one's going to be the weird one, and some of you are going to catch on. It is 2 significant figures. Okay? So when you look at your answers and you look at your math, something may click there. And I don't expect you to know it yet. I have not taught you the concept. Guys, I do this a lot. I pre-teach stuff because some of you are going to grasp it. And when you actually see it, it will definitely click. Okay? Remember he told you y'all sit there with those Velcro helmets on? I told you that? That's a Velcro ball. Just flung at you. What's wrong? You're overanalyzing. It's what you're making it a lot harder. Colby, tell them it's a lot easier than it sounds. It is. I'm telling you, it's a lot easier than it sounds. Say that again. It can be. It can be, and that's what I'm saying. We'll get there. Don't stress yourself out. Listen. I'm going to teach you everything that you need to know. I'm never going to leave you hanging. Now let's look at number 4. Number 4 gets a little weird. It says 25.2 milliliters of water are placed in a graduated cylinder. Visualize that. Got a graduated cylinder. I put all that water in there. Then it takes a 22.6 gram stone and we drop it in. And this is the key phrase. The water level does what? It rises. Oh my goodness gracious. It rises to 34.2 milliliters. So find the stone's density. So let's start with what we know. What is the question? What are we trying to solve for? Density. I don't care about the rest of that stuff written in that question. I need to find what the question's asking me. And I know that density is what? Mass over volume. So let's start with what we know. We have 3 values in this question that we've got to worry with. Are any of them able to be used as written to be plugged into our formula? Which one? The mass. Because it's straight up 22.6 grams. So 22.6 grams. Now, why can't we take the milliliters and just plug it right in? How many of them are there? There's 2 of them. Well, I'm going to ask a dumb question. Which one is it? It's a trick question. It's neither one of them. What is this called? Water displacement. Okay? So how would you find the volume of that stone? Subtract. Now this is important. And if you want to write it out over here, you may want to, so you need to write final minus initial. So the important part was, what was your final volume? Okay? So we've got 32.4 minus what? 25.2. And those are both milliliters. And so what we get? 7.2 milliliters. 7.2 milliliters. Now can we plug it in? Yes. Okay. So take your calculator, plug that in, and write down your hypothesized answer with correct significant figures. Some of you are getting it already, and that's awesome. If you're not, I promise you, life will carry on and you will get it. Don't stress over the significant figures. Obviously, that's a terrible answer. So my question to you is, how many of you just wrote 3? How many of you wrote 3.1? How many of you wrote 3.13? 3.14? Okay, 3.139. Here's the correct answer and correct sig figs. Chloe, will you let him in? How many significant figures are in my answer? There are 2 of them. It has something to do with the decimal. I do. Today's tell the significant figures are easy. All right, now, if I leave that red number alone, it is wrong. Gram per milliliter. And again, don't just assume that it's one part of the fraction or the other. It may not always be that way. All right, guys, you do number 5 all by yourself. Do number 5 all by yourself.